Okay, so welcome people of the mathematical physics seminar in Prague. Our speaker is Panagiotis Batakidis, and he's going to speak about Atiyah classes in geometry, representation theory, and mathematics. Please.
Okay, thank you so much. Thank you, Brandon, for hosting me. So I'll tell you a small story. This basically the main part of the talk. So first we'll do a little brief historical review of the main instances of how the class was introduced, and then for almost like 40 years, nothing really important happened. And then after Panagiotis and Kapranov, the whole thing exploded, and we'll basically focus on that part after in the last 25 years. And after that, basically, I will say a few things about how we look at the class right now and why it's interesting and what you can think about it, or at least what I'm thinking about it. Okay, so the slide is about a little bit more detailed introduction. We still haven't started yet. I will explain exactly the original setup by Atiyah, how this class was first introduced. That will be right after the slide. And then we'll talk a little bit about why we are now interested. And as I said, this because of these two researchers, Panagiotis and Kapranov, simultaneously in the same journal issue published two papers containing major breakthroughs about the class in different dimensions. But I will explain that later. And the third bullet is it's on the recent and modern view of the class, and I will use this language to describe it, this DG differential geometry language, to describe it and state a few of the most important lesson results. Okay. All right, so this is me on my way to explain what the Atiyah class is, at least for homomorphic vector bundles. And the basic ideas, this and the next slide, will be following us throughout the whole talk. So when you have a convex manifold, you have this splitting the complexified Thousand bundle into these two eigenspaces, and this produces splittings in all the differential geometric related standard objects like connections and the covariant derivative of that thing. So this is my notation basically. 0, 1, 1, 0 is just there to tell you which part of the decomposition you're increasing every time. It's standard notation. And this outline Nuremberg theorem saying that whenever you have no, it's not exactly that. So it was about minus tensor. But whenever you have a convex manifold, this is equivalent to saying that this partial is 0, one part of your derivative is actually a differential itself. So since you have this differential, there is a related cohomology theory. That's what we call the double cohomology on this bigraded complex. And this is the cohomology theory where the Atiyah class that I'm going to build slowly now is going to live. Okay, so in this first original setup, the Atiyah class is just a double cohomology class in the first degree of this cohomology. So what is it exactly? Now, here comes the problem the Atiyah class describes or wants to solve. Okay, for me, a homomorphic vector bundle will be just the data of a vector bundle E together with a T01 flat connection. Okay, so later on, we'll call all these guys will be called simply representations of some Lie algebroid. My example here, the Lie algebroid is T01, and I will be calling E just the representation, the Lie algebroid of T01. Okay, so you start with this guy, just the flat connection on E. And then you can extend this T01 connection to a connection of the entire complexified quantum bundle next, just by adding some component for the other guy T10. Okay, and of course it doesn't necessarily, not necessarily flat this connection, but I'm putting these two together and I'm building a connection now of TX on E. And of course, again, this is not a flat connection necessarily, but if you look at this curly R, the curvature of this guy, this curly R is just the curvature of this guy. It belongs to in this one space with values in the endomorphism, and it's actually the ordinary definition of a curvature operator with these entries. And you can show that this is actually it defines a homology class, which is, that's the key point here. It's independent of the way you extended your original flat connection. Okay, so in whatever way you choose this T10 nabla 10 extension of the flat connection you had in the first place, this will always be describing the same cohomology class. And this class is what we call the Atiyah class of the homomorphic vector bundle. And in reality, it's actually, and you will always be this talk an abstraction class for the existence of some geometric structure. And in this case, just the existence of global, it measures the abstraction to the existence of global homomorphic connections. Only because locally you can always do that.
I'm so sorry, but from online we can barely see the screen, what you're projecting right now. Would you mind sharing the slides on Teams, please?
Or if you could do what you did last time to improve the quality. Remember? I think there was a similar problem last time.
Back the camera, so hopefully that works.
I think there's no chance to improve it. I share the same. I cannot see nothing. I can see anything.
So you can see the presentation, but I mean, the problem is you're not seeing the slides at all.
No, so we see just this camera as it's taking video of the slides, but the quality is too low to read anything.
Maybe you're sharing your camera.
Yeah, if you can share the screen with slides instead of camera, that would be, yeah, perfect.
Yes, so I thought I was doing that, so it's my bad problem. So I'm sorry. Can you now see this the actual slide?
Yes.
Okay, so this works. Okay.
Yeah, that's. I think that's perfect.
Okay.
Thank you.
Okay, so there were a few things happened in the meantime, but I will move fast forward 40 years now, from 57 to 97. But before I do that, let me give you some introduction to understand why that was what Panagiotis did was surprising. Okay, so the introduction is about a few things that were actually mentioned yesterday by Thomas in the class. That was a nice coincidence. We were not in agreement before. So I will skip that because I'm assuming more or less the standard Lie algebra, universal Velikin algebra, symmetric algebra, and so on. You can think of these two guys as distributions on different objects, like around zero for the symmetric, around the zero of the Lie algebra for the symmetric algebra, and around the identity of the group for the universal enveloping algebra. But the whole point is, again, Thomas mentioned yesterday, is that when you take a symmetrization map, PBW map, this is only a vector space or G-module isomorphism. And the problem, if you want to turn it into an algebra isomorphism, and I will not explain why, is that you have to compose PBW here with this very strange thing. It's a very strange feature over there. I wrote a little bit the definition there. If it's not making too much sense, that's reasonable, but at least you just think of it as a differential operator which acts on these polynomials. We first have to take a polynomial here, hit it with this infinite order differential operator, and then the result you'll get, you push it forward with the PPW map, and this actually is an algebra isomorph. So where this thing comes from is it's a long story, and it's not our something today, but this was the original result by deploying in 1970s, and this is a standard theorem.
So what you have to change, of course, the product is magic algebra.
Say that again.
You have to change the product to magic algebra.
Now or
So yes.
well, here I'm using the computer product. When I will write it maybe in the next line as quantized version of QT, then I will put in the star product. But here you don't have to do that yet. That's the whole point. If I just had the symmetric algebra with the star product, that would be an algebra isomorphism. But still I'm using the computer product here. It's just a map of object to some other object, which is not a
So you not get the map.
I'm restricting to environments, so you don't have a problem with commutativity.
Okay.
It's not a nice model between ST and GG, right? If you're restricted to environments, everything is commutative, but still it's not an algebra. Okay, so if you know what Panagiotis formality theorem, that's fine. If you don't, I will just briefly give you the idea. You have two main objects on the second bullet, polyvector fields on RK and the algebra DGLA of polydifferential operators on RK, and you show that in appropriate cohomology theories, these two the cohomology theories are isomorphic, and this is what is the terminology, and then we say that these complexes are quasi-isomorphic. Okay. The map producing this quasi-isomorphism is very complicated to write down and describe, but if you restrict it to some to the first degrees of these cohomology theories, then you get exactly as a corollary. In this paper, the third bullet is actually just a corollary around the end of the paper. You get the diploid isomorphism that I talked to you before, and in fact, the isomorphism of cohomologies that I'm writing here is a bit more general. If you take this isomorphism in degree 0, that's exactly the closed theorem that I had before. So here's a more general version, but the idea is always the same. And since then, I wrote this just for you to see. I won't talk too much about it, but this was explicitly written down in a book. The whole proof was written down in the book by Kalak and Rossi. And for complex manifolds, for example, the way the Atiyah class that we saw before, the way it works is exactly to produce through the dot class of your homomorphic vector bundle composed with the Hochschild Kostner Rosenberg map is to produce an isomorphism of this cohomology. So you have the dot ball plus something cohomology over here and a shift of the dot ball cohomology over there. This is just for you to see. We don't care too much about it. It's a very nice book if you really want to go into the details of this generality, but I will skip it. So that was about Panagiotis. The other big breakthrough around the same time was Kapranov, and it's also still very interesting, and people still are generalizing this result. Who basically said that in this original complex case, these Atiyah class fields essentially a Lie algebra object in this derived category. Or more generally, well, you have something stronger for a Keller manifold. You have actually infinity algebra in this resolution of TX1. Now, both of these things, after maybe 20 years after Kapranov and Kontsevich were put into a common ground diameter the ground of Lie algebra. So I'm assuming everyone here knows what a Lie algebra is. If you don't, just think of a many object generalization of Lie algebra. It's not just a bundle of Lie algebras or a manifold, but it's something that, if you restrict to a point, gives you a Lie algebra. It has all the nice properties of the tensor bundle, meaning the properties of the tensor bundle, if you want to think of it that way. Okay, so the way to put all these things that I showed you before in one setup is to think of Lie pairs. Here's some examples of what a Lie pair is, which is something very simple. It's just a Lie subalgebroid of a big subalgebroid. I will call them L and A. Again, if you restrict over a point,
That's a brand.
a pair of Lie subalgebra and Lie algebra. If you have a regular formulation, this is also a Lie pair. Your big Lie algebra is just Tm, as with tensor bundle, your formulation or subalgebroid. And there are very nice, other nice examples of Lie pairs. Our first original complex case is also a Lie pair, right? So, in what I'm going to do in this general setup of Lie pairs, whenever you restrict to this example, you will get the original Atiyah class back. So everything is compatible. Okay, so this is how we're going to generalize it here. As I said at the beginning, a Lie algebroid representation for us will just be a flat connection of a Lie algebroid to some vector bundle. Okay, just ordinary connection, linear on the lower argument, first order differential operator on the second argument, controlled by the anchor. Okay, so a flat connection is a representation in this category. And the most famous, the simplest example is the bond connection, right? You just apply all that to a very simple vector bundle, equation of L over A, and just your bond connection is just projection essentially to the equation. Okay, this is flat. This is a Lie algebra representation of A. And before I show you, this is something like not okay. Let's make a pause. Just to, I couldn't find a better place to put it in this slide, so it's here right after representations of Lie algebroids. To state the result that I want to later, we have to know a little bit what the representation up to homotopy is, which is the same, roughly the same idea, except that you don't have a nice curvature that vanishes directly on the first layer. You have higher orders of higher terms of curvature on a graded vector bundle on which you have this flat A connection, but this is now a super connection, as we call it. It has many components. So all these different parts of the curvature that don't vanish exactly, they vanish up to some terms, and they have to satisfy these conditions, these compatibility conditions. You don't have to remember in detail what a representation of the homotopy is. It's just that, just remember that it's a many object thing. It's a gradient vector bundle, and you have a connection on that vector bundle whose parts of the curvature vanish up to some terms. Okay, that would be enough. I will use this a few slides later to state the result. But if we go back to what Lie algebra, just plain Lie algebra representation is, right? We say that this extended connection, and I did the same as I did for the complex case before. I started with a flat A connection on E, that's the main module, and I extended it to some connection nabla of L on the same guide on E, and I'm taking this part of the curvature, the one I'm who's denoted RE nabla. Okay, this is the part of the big curvature. So this connection is said to be, this is the definition, this connection is said to be, let's call this, from sections, right? Sections to I think the big convention is said to be A-compatible. Right? If of course it extends the A action, otherwise it will make no sense. This is not, it's almost not, but it's called A-compatible if this part of the curvature vanishes. Right? What I'm writing over here is just for this guy to vanish. I'm taking, you see, I'm taking arguments of these two guys, and I want to vanish.
You're saying that this will vanish, so here there's some
Yeah.
equals.
Oh, yeah, sorry. Yeah, thanks. Okay. So this is what I will be referring to as the standard Atiyah-like theorem. This is the type of theorem we want to prove every time you have a cocycle in some cohomology theory, and you want to call it the Atiyah cocycle of something. Right, I will say it in this case, but all the later Atiyah theorems that you will see, they're all modeled on this result. So first part is to show that your guy is actually a cocycle for a nice cohomology theory. And of course, this cohomology now is just a Lie algebraic cohomology of your original Lie algebraic with values in this module, because obviously this is a module, this L over A, the dual of L over A, the main module. E originally is an A module, the endomorphism of E is an A module as well. The tensor product is an A module. Okay, so you bring this Lie algebraic cohomology, you have a cocycle in it. You have to make sure that this cocycle is the class it produces is independent of the extension you're taking, right, to get the big conduction, and that it vanishes exactly, your class vanishes exactly whenever, if and only if there exists an A-compatible extension of this convention. Right, so this is what we'll be trying to do in the regular case, I mean the ordinary differential geometric case, not the gradient geometric case. And this is by the same people. Sensing on the two. This is the analog of Kapranov's result stated in the language of Lie pairs, right? You can see it's saying basically. Okay, so for Lie pairs, now forget that we have this different complex case, the regular foliation case, and all that. All these guys, all these situations, I will see them as examples of the Lie pair case. And at least for regular foliations, this is what vanishing of the Atiyah class tells you. Right, so I'm taking this pair, Lie pair, TM, and the tensor bundles to the regular foliation, and the class, this class basically measures this obstruction, right? Existing transversal connections preserved by parallel transport. In this example, this was something actually known from the 70s or early 80s. This before this work, this was called the model. For regular foliations, the model class is exactly what I described over there. That was something known, but Gilles and Mathieu just recovered it in this general setup of Lie pairs. And this is an example that you can compute by hand. Actually, the cocycle that I described before in this very simple example of Lie pairs, which now just an example of Lie algebras, gives you a generator of this one-dimensional space, right? First degree, the homology of that. Right. Okay, this was just an example, but you can do it by hand at least. Okay, now let's switch to graded world. I will recall a few things, mostly definitions, to get into some examples for whoever is not familiar with that. So we will just call them graded manifold. I'm assuming it's C-graded manifolds. It will be just a manifold whose sieve of functions over some open set looks like that. So you could have C-infinity coefficients. That's what the easiest way to think of it. You have C-infinity coefficients in front of a formal power series of terms in some fixed vector space star. Okay. So the DG manifold is just a graded manifold, the one that you have before, with some derivation of these functions. So it's a vector field. You can just think of this guy Q over here with two conditions. It has to be of degree 1. Everything is graded in this graded world. So all your functions, your forms, vector fields, everything are graded. So it has to be degree 1 and with a 0 square. So immediately, the way I'm defining this Q is essentially like a combinatory operator that will be a differential if I think of a nice way to represent my functions on this gradient manifold. And the easiest way to get you convinced that this is a useful way to think about things is this list of examples. Of course, every time I will reproduce a cohomology theory, but this is not trivial to me. So take the easiest example. You have a Lie algebra. This curly M is my graded manifold. Is a DG manifold actually because my functions, the infinity of curly M that I'm writing in the second row is actually the convex of the set of forms, exterior algebra forms on T. So the homological vector field that I constructed before is actually exactly the same as the Sevali-Allenberg differential of G. So if you only have a point, your manifold is a point, you get the Sevali-Allenberg or Lie algebra homology. If you want to generalize it, you get a Lie algebra homology. It's just one example of the whole construction that I was describing before, right? So you see, even in this first example, very quickly you get all this previous stuff easily read. All smooth manifolds give you a DG manifold with the obvious. I think the idea will be pretty much straightforward by now. So your DG manifold is just a shifted Thomson bundle, right? Shifted by 1. So you give a degree 1 to all these guys. You take functions then of all these guys are exactly differential forms, the convex of differential forms, which your theorem differential, which is represented by homological vector. You think of this as a derivation of these algebra functions. Okay, and this can go on for quite some time. Complex geometry also can be looked at in this setting. This is my DG manifold, differential gradient manifold, and this is the complex where I built the double operator on the first slide, right? And this is exactly what my homological vector field is. So when I will now start talking about DG manifolds in the Atiyah class of DG manifolds, I'm doing all this stuff many more at once. But before the standard, again, Atiyah-like theorem, just let me give you one piece of definition, which is nothing really very extraordinary or something you wouldn't expect. Remember, now you have a DG vector bundle is a way to think of it. It's okay, a graded vector bundle, that's easy to guess that it should be. What is the differential operator now is you think of A as a manifold, a graded manifold, right? And you want a homological vector field on it. That's all. You keep the same idea, and then the DG Lie algebra is exactly the same. Now you have two let's say differentials that you have to that are playing around. The one comes from the differential gradient structure, and the other one comes from the Lie algebraic structure. The only condition there is that these will have to be in some compatibility relation between them. So they have to be nicely together. So having said this, this is again the standard. You will look at 1, 2, 3 these items. These look very much like the standard Atiyah theorem that I showed you a couple of slides before.
Sorry, do you hear me?
Yeah.
I have a question. What is this DL? QL, you say it's the Lie algebraic structure. What is DL?
It's the Lie algebraic differential of M.
Ah, of M.
Q,
Okay.
right?
Yeah.
Q is a vector bundle, DG vector bundle structure that we had from
So
above.
this curly M is supposed to be Lie algebraic, or?
No, DL is for the Lie algebraic, QL is for the DG vector bundle structure on which you're building the Lie algebraic structure.
But again, curly M is supposed to be a Lie algebraic or not?
Curly M is not a no, it's not. Curly M is not a Lie algebraic.
So it's
L
L.
is a DG vector bundle, and you have a Lie algebraic structure on this DG vector bundle. This Lie algebraic structure has a Lie algebraic differential, that's DL. And QL is the homological vector field of the DG vector bundle L.
And DL is again what?
The Lie algebraic differential of the Lie algebraic structure.
Didn't get it. Okay. Doesn't matter.
Yeah, yeah. Yeah, yeah. Okay. Okay, so okay, first look at the data that you want to have to build this map curly A. Okay, before we go to the statement. So you want a DG algebraic, right? Look here how I set it up in the original Lie algebraic case. That was originally just a simple Lie algebraic. I'm asking it to be a DG Lie algebraic now. That was originally just a vector bundle. I'm asking it now to be a DG vector bundle. Okay, and I'm having a connection, right? Of L on right? And now, what this cocycle, what is going to be proved to be a cycle is essentially what I'm trying to write over there. It's just a derivative of the connection, right? Or deriving the whole, and that's why these two guys, QL and QE, have to be in this nice compatibility for this to make sense. You're deriving a connection, the result of the connection, and then you're deriving each one of these terms with the appropriate homological vector. So the theorem says that this is actually what is supposed to be, in the sense that okay, the first two are more or less more straightforward. That is the degree 1 section of the right space, right? Morphism, homomorphism of the pair to E. And it is one cocycle now for the DG Lie algebraic of L with values in this one cocycle for this, let's say, homological vector field. So this one is something that you build as I did before from the data of the two homological vector fields that I have on the definition. You combine them together to build a homological vector field on this entire guy. And the remarkable statement of the theorem is that the class this guy induces is independent of the connection, right? Whatever connection you start with, essentially, it's the homological vector field that will tell you what the class is. Okay, so now I'll just start referring. Maybe I have to bit fast. We'll start referring to a few theorems from the last decade. This is something we did with Yannick some years ago. And it basically says that in the original hits, so that was still the time where people were making the passes from the ordinary lead pair setting to the graded setting. So we had to convince ourselves that somehow the objects we were using were making sense. And this is basically a result in that spirit. And the idea for this is to ask and say what is the right graded geometric object you need to have if you want to really reshape or repackage the whole Atiyah class of lead pairs business. And what we're saying there is that this graded object is actually this direct sum of L simply by 1 plus L over A. Why is this the natural object to think of? Because then the two natural operations of inclusion and projection are actually these manifold morphisms. And that there is an appropriate DCL algebra on this thing so that the two realizations of Atiyah class, the graded one and the classical one, let's say, make sense in the sense in which way it makes sense. In the sense that this I exactly this quasi isomorphic between the respective two cohomology theories, and since the DT geometric Atiyah class living on H1 in the graded world to the Atiyah class living on H1 in the algebra cohomology effect. Right, so there is a quasi-isomorphism that relates directly these two Atiyah classes. That was the next one is a bit more recent. Okay, that was built by many people, essentially, but not really at the same time. But for the result that I'm going to show you next, we mostly were based on Shanyi, Yao. So what Mathieu, Sebastiano, and Sue did was to describe essentially this construction through a very simple object, which is just a pullback of there's a complicated pullback construction that for every pair gives you a DCL algebra. It's not exactly the same that I had before. Whose total and Atiyah classes are identified with the standard classes we have for lead pairs. I didn't say anything about the total class throughout the talk. We only saw it at the beginning when we had consensus theorems. But the idea is that whenever you have a nicely defined Atiyah class with this type of operator that I showed before, taking exponentials and the determinant of some nice operator, then we have also a nicely defined total class, which, at least for me, is not as rich geometrically. I mean, maybe in some index theorems you could use it, but this is not known yet, to be honest. Like all index theorems in this graded differential graded geometry world are not so developed yet. Okay, so Shuangyi Yao very soon after them just simplified this construction very much, basically using a complicated version of perturbation lemma. And this is what we actually used ourselves with Sylvain last year to have an Atiyah-like theorem, very shortly writing over here. We use this to have an Atiyah-like theorem for lead pairs again, but representation of something other. So this is like generalization of the lead pair case for super connections. Again, you see we have all these different parts of the connection, and the condition is that the curvatures have to satisfy all this the series of equations. But the idea now, generalizing this, is that you get a class that it has different components. It's a cocycle. This class is made out of different cocycles of each one of these curvatures, and all of them they can be made to live into some nice homomorphism theory for which this guy is the differential, and satisfy a theorem that has those three items that I showed you before. In that, okay, I'll tell you maybe now what the idea was before. Our first, not our first goal, but our ultimate goal, as I was explaining before, is to define, and this is an open question, still an open question, was to define and understand what the Atiyah class of singular formulation. Because for regular formulation, as I said, it was already known by the 70s. That's the model dot class. All right. This is still the same class, nothing changed. It's just rephrased into more elegant, more concrete way for leapers and then very difference of geometry and so on, but it's still the same class, nothing changed about what this guy is doing. But for the singular formulation, this is not at all known. It's not even defined yet, much less understood. So our original motivation was to try to define something like this, and you may see this theorem as an intermediate result, because essentially we're taking finite DT vector bounds, so this representation of the homomorphism is a finite length, any length you want, but just keep it finite. And then in some examples of short lengths, like 2 or 3, we could actually have the actual computations and show that you could reproduce what you had before for representations of the homomorphism that can be built by classical examples. So as an intermediate step, this is okay, but this is still, we are still a long way from this guy. Okay, I really have nothing much to say about some things that are probably involved. Would be the whole point of the singular foliation, in the sense that, okay, one idea of very informally, one idea of what this guy would be or might be is that it's zero exactly when the formulation is regular, right? Otherwise, it cannot be zero, because as the original model class for regular foliations, it controls the homogeneous of the foliation. So if the foliation you start with is regular, then the class that we are supposed to construct will be zero. But this is just a speculation. I'm not really sure that this holds true. I hope this time I have something more to say. Okay, yeah, something that might be also interesting to some people here is this result by, again, Rods, Mathieu, and Ping. Remember this is in the same paper that the DT geometric Atiyah was introduced. So that if you have a torsionless connection, then you have actually a link to the algebra structure on this tangent bundle, the tangent bundle for DT. And this basically, in my opinion, without knowing the details in much depth, it basically is applied to the thing that I showed you before. So the 2 point, the first thing is that the first part of the structure is just the derivative with the homological vector field. And the second part that's almost in bracket is given by the cosine, the Atiyah cosine. And we thought really, I think many of you know more details than me about what this field says. I'm just stating it here to show that it is probably, it has very probably much physical association to what you know interested. So this is by Lara and Thanasis. It says that these two guys, the great geometric objects that are related to T1 shifting the tangible of T sigma, these two objects, the homological vector field and the Atiyah class, contain exactly the information about the transformations of gauge symmetries of this case figure. So more or less, these are the results I want to stress out. And here's a list probably of almost exhaustive list of what I'm thinking about these objects that I have over here. I will not say more about the Atiyah class of the singular formation. I already discussed this. The other thing is the Atiyah class of the non-impaired. Again, related to the talk some of you heard yesterday, a non-impaired is just the data of a current multiple E with Dirac structure D. Very, very briefly, very sketchy, the difficulty to extend these ideas to many pairs is that these two things are not in the same category. Right? So before we had a leap pair, everything was living in the linear category, homology, cohomologies, and everything. These two guys are of a different nature, and it's, we have some work on that, but it's not finished. With the ultimate goal, as I was explaining before, to have the example of complex geometry that we discussed, but some detail in the talk, generalized to generalized from this. Right? So you know how this works now for the Atiyah class and what it measures, which obstruction it describes and all. If you want to apply, if you want to have such an object for generalized complex geometry, you're forced to build something that is for a man impaired. And we'll just apply this to the standard code algebra. And then there's a few questions from the homological side of the screen. Basically, that if I take this Lie algebra object in this derived category that Caprano is saying that it exists, what happens if you take a Lie subalgebra object? What's the geometric object that corresponds to the smaller class, let's say? This is completely unknown. I have no idea what the answer might be. And in general, something that I'm like personally to see in the future that would be very interesting was to transfer all at least the standard setting in derived differential knowledge. Right? I'm also not an expert on this stuff, but it's something that it seems to be very interesting with many applications. So I hope I didn't go too fast, but I think my slides are done. So thank you very much.
Nice talk. Are there some questions or comments? Also for the online people, if you have questions, just unmute yourself. yourself and ask, please.
So as like an example of single foliations, have you heard of like positive manifolds?
We don't really care where the singular foliation comes from. It could just be like an action of a liquid on some manifold. If it gives you singular foliation, that's enough. And these are the first examples, like these examples that we're looking at. But still, it's not so clear what it should be. I mean, we're that early in this discussion. Like even if you take like R2 active upon SO2, we still don't know how this works. What is the Atiyah class of this foliation of a point plus concentric circles? We don't know.
I think that Boston homology might have something to do with.
Yeah, I would say it makes sense. Yeah, it could be. There are different reasons why people think that boson homology is more rigid. Let's say in real topological homology. I don't know. I don't know. I have no idea. Right? That's to be honest. I have no idea.
Is there a version of Atiyah single that you
Of Atiyah, what?
of Atiyah single type of zero?
Yeah, no. No. Oh, for singular foliation.
That is conjectural, you know, how you try to relate topological objects with analytical.
Well, in the sense of like a bound constants. Yeah, these are done.
This is done.
This is done. Yeah. There's too much work on that. Yeah. I don't. Okay, I understand up to some point, but for a large class of singular foliation, this is no.
Okay. Are there more questions? Let's thank Amos again. See you next week.